Okay, when objects are accelerating, it does make things a little bit more challenging in terms of trying to find things like displacement. We've already gone over the equation on how to find the changes in velocity, but when objects are accelerating, the displacement does definitely follow a pattern, but it's not quite so obvious. So we actually have a couple of different formulas that we can look at when looking at position or displacement of objects while they are accelerating. We'll just kind of give you both forms here. To begin with, let's just say we're looking at the overall displacement. So from start to finish, kind of what is the overall change in position of an object? It is going to depend upon two things. It does depend upon whether or not the object has an initial velocity, right, this v0. Because if it does have an initial velocity, that is going to make it travel displacement. Plus, we're going to have another factor because of the acceleration. And so this entire equation will combined tell us the overall displacement of an object if it does have an initial velocity and an acceleration. We've already gone over what each of these symbols mean in the earlier videos, so I don't think I need to diagram them all out again. I will just run through them though. This is the overall displacement of the object. It could be positive or negative, depending upon if the object's moving forward or backward, upward or downward, depending upon what we're defining as kind of our positive and negative directions. V0 will be our initial velocity, the velocity at time equals 0. The t here is the overall time interval. This is the acceleration of the object. Once again, we have to assume in this situation that the acceleration is constant or about constant, and it's not going to change very much. And then this is the same time interval we had before. Sometimes this time squared factor gets a little tricky for people. Once again, in terms of how to do the math, it is only the time that is squared, right? So you don't take half times acceleration times the time and then square that entire quantity. It is just the time interval that is squared multiplied by 1/2 of the acceleration. And then to that we add this. So I always kind of break this problem into pieces. And when doing the algebra, I'll do this piece first and actually write down what the solution is. I'll take half of the acceleration first, write that down, square the time, write that down, multiply these two numbers, and then add it, kind of work backwards and add it to my original number. Once again, if you want to just put this all in the calculator in one big line, you can do that. But you do need to make sure that you put parentheses and things in appropriate places so that your calculator will do the proper order of operations. Like I say, I just kind of diagrammed how I do the math. Obviously, you can do the math however you want. That is the method that tends to work for me. So when would we use this formula? Well, anytime we are looking for displacement of an object, when it is accelerating, and we know the time, because those are all of the factors that are involved with this. There may be cases when we don't really want to know the overall displacement, but actually an exact position. Right? So we have a different formula for that. It looks very, very similar. The only difference with this version of the formula is we know the actual position number we're starting at, meaning we've kind of diagrammed out some big long number line, and we're know at position like right here, whatever that is, right? That's x0. Xt is not going to tell us overall the displacement. It is going to tell us on this number lined exactly where am I after this time interval. If the displacement is positive, we might be over this way at whatever our final position is. Overall, if our displacement is negative, we may end up over in this direction somewhere. Right? That might be where our final position is. So this formula doesn't tell us really how far we moved. It tells us on this number line exactly what position are we located at. So x0 is what position did we start at on this big number line thing. It usually makes the most sense that we set that to 0, but it may not be the case. I mean, we actually may be told we start at position 27.3 meters, and then this stuff happens. What is our final position? And then that would be the formula for that. Okay, so what would be an example of when to use this? Let's just say we have this problem. A ball is thrown upward with a velocity of, let's say 42 meters per second. Okay. What is its displacement after 4 seconds? So 4 seconds after I've thrown it, what is its displacement? So in this case, we're going to be using the top one because we're actually talking about an overall displacement. Instead, I could have said, if the initial position is 10 meters, what is the final position? In that case, we would have used this one. We would have put in 10 meters for the initial position, then worked through the math. Right? But in this case, I'm just looking for the overall displacement. Now, there's also a couple of hidden things. With all of the problems so far, that there are things that we need to look for, like at rest. Something starts at rest, which would mean the initial velocity is 0. In this case, something to look for is thrown upward, thrown downward. Anytime something is thrown and going through the air, there's something that's hidden within this that isn't necessarily always stated, because as a physics student, you're just supposed to know. Right? If something is moving through the air, it is always accelerating because of, ding, 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 you're exactly right, gravity. And so the acceleration due to gravity, we'll start using the exact number, is to 2 sig figs anyhow, negative 9.8 meters per second squared. Negative because gravity pulls objects down. Right? And so our downward direction in physics is negative. So we do have this hidden acceleration value inside of our problems. Right? If we're kind of diagramming out, annotating this out again, that would be the acceleration. 4 seconds would be our time interval. 42 meters per second is our V0. And we're looking for the displacement, which is triangle X. So once again, kind of diagramming, annotating things out. Let us know what's going on. So I need to watch. I actually am off camera a little bit here. So in case you didn't get the entire statement, I think now you can read it. All right, and so this is what it looks like. So triangle X is what we're looking for. V0t, 42 meters per second, times 4 seconds, plus 1/2 times negative 9.8 meters per second squared. And that's one of the most important things. You have to make sure you carry the negative along with the acceleration value. And then it is 4 seconds squared. So then we do the math. 42 times 4 should be 168. And the seconds and per seconds cancel, so that's meters, plus half of negative 9.8, negative 4.9 meters per second squared. 4 seconds squared is 16 seconds squared. And then this is going to be, we got 4.9 times 16, 4.9 times 16 is 78.4, negative, because this is a negative, right? And then I'm going to add those together, and we get 89.6 meters. Kind of skipped over the fact, once again, we have a per second squared and a second squared, so they are going to cancel out. So this is negative 78.4 meters, adding up 89.6 meters. With sig figs, we haven't talked about that yet. We probably should. There are 2 sig figs in this number, 2 in this number. If I can kind of cheat and go backwards, we'll make this 4.0. Right? So there's 2 sig figs in that answer, or in that number. So in our answer, we should keep 2, which would be 90 meters, actually, to 2 sig figs. So that's how we would work that problem. Okay, I'm going to go ahead and actually do the last acceleration formula along with this one. And that acceleration formula also kind of describes what's going on with velocity and displacement, only in this case we don't know the time. And sometimes that happens. Sometimes we're able to measure things like the overall displacement of an object. We'll know the velocities or the acceleration, or we're looking for one of those facts, but the one thing we have no idea about is the actual time interval it took for that sort of a change. And that formula is this one. Once again, we've kind of defined all of these things separately, so I don't think I need to do it again. So what we have is our final velocity squared is going to equal our initial velocity squared plus 2 times the acceleration times the displacement. And this is actually a combination of this equation along with just the actual acceleration is the Vt minus V0 over time. We actually solve that equation for time, put the time in here, do a bunch of algebra, and we can actually derive this equation when the time all cancels out of the other two formulas when we combine them together. So, as I said, this is something where we can look at the velocities, the acceleration, and the displacement, and not necessarily have to know anything at all about the time that it takes. So, for instance, let's do this. Well, we'll do a similar problem to the last one. Here we'll say a ball is thrown upward. We'll use the same numbers with a velocity of 42 meters per second. What height does it reach? In fact, I should probably say maximum height. I mean, that's what I mean. What is the maximum height it reaches before it turns around and comes back down again? So a ball is thrown upward with a velocity of 42 meters per second. What height does it reach? What's the maximum height that it reaches? And see, the one thing I don't know about is what time does that take? But actually, I don't need to know that. I really could go back if I wanted to, work through this and find out time. It would be actually a quadratic formula that I would have to do, and it's really kind of messy. But as it turns out, I don't really need to know the time to answer this question. So diagramming things out again, kind of annotating things, I really only have one number, which is the V0. All right, but once again, thrown upward, okay, that's going to mean my acceleration is negative 9.8 meters per second squared. And there are a lot of times when you are not given really all the information you need because, once again, you're expected just to kind of reason things out. Right? So we're missing two things. We're missing the height or the displacement. What is that maximum height it's going to reach? And we're also missing what is this final velocity. So if all else fails, I suggest we kind of diagram some things out. We're starting at 42 meters per second. We're throwing this thing upwards, and that ball is up here, or object, whatever it is. I want to know what this displacement is. When I'm looking at Vt, it's like, what is the velocity right there? Because even though I don't know time, Vt means at that point in time, wherever we're looking at something, and here we're looking at that displacement right at that point in time, what is the velocity there? And I am expecting you to kind of remember, you throw something up, when it reaches that maximum height, guess what? The velocity at that point is 0. As we talked about, it's still accelerating. This acceleration is still there, but the velocity is 0. So that's our Vt. So now we have all of our numbers. Okay? So Vt is going to be 0 squared equals 42 meters per second squared plus 2 times negative 9.8 meters per second squared times the displacement. Right? So that displacement will give us our actual height when the velocity is 0, which should be the maximum height. All right, so 42 squared is going to be 1,764 meters squared per second squared. Get our 0 out in front of here. Right, when we square units, we square both, right? We're going to square the meters and square the seconds. Meters in the top, seconds down below. Plus negative 19.6 meters per second squared. 2 times 9.8. Triangle X. Doing the algebra, we're going to subtract and bring this over. They're being added, so I'm going to subtract and bring this over. Negative 1764 meters squared per second squared equals negative 19.6 meters per second squared. Triangle X. Bring this over and divide. Isolating the variable, as the math folks would say, right? Isolating the displacement, those go away. So then we're just dividing. Divided by 19.6 is 90. So 90 what? Well, the per seconds squareds cancel out. This meter cancels out the meter squared. We are left with meters. 90 meters high, which is about 280 feet. So if you could actually throw something with a speed of 42 meters per second, it will go approximately 280 feet high at that point, right where it stops and turns around and comes back down again. So those are just some examples of some of the formulas and the types of problems they're used for. Just to kind of review, right? Anytime it says constant acceleration or something is constantly accelerating, either positive or negative, and we're looking for displacement and something with the velocities, but we don't know anything about time, this is the rule. Right? If we do know something about time, or if we're somehow interested in time, time might be what we're looking for. If we have displacement and velocities, right, and acceleration, you know, it's one of those. Either we have the velocity, or excuse me, either we are looking for the displacement or some actual position. That would be that formula. If we're looking for just velocities and acceleration, we don't really care about displacement, just looking at how the velocity changes over time with acceleration. Right? It's one of these two versions of this formula. Once again, mathematically they work out the same. It just depends upon which factors we have and which ones we're looking for in terms of which one we might use. And then finally, when we're not accelerating at all and have some sort of constant or average velocity, it goes back to this equation. And depending upon the situation, it may actually be a combination of several of these, depending upon how complicated the motion is. Right, we've gone through several problems in class where something is constant velocity for a while and then accelerates, or it could be accelerating at one rate and then is constant, accelerates at a different rate. And so actually you may be breaking a problem up into several different sections, and each section may have a different formula they're going to use. If there are more questions, I mean, by all means, there's Khan Academy. There are other YouTube videos covering some of these things. Otherwise, just make sure you ask lots of questions in class, and we'll work through them as best we can. Thanks for watching.